welcome you to my lecture today. Today, we're starting a new topic. We call that two-way and any-way analysis of variance. Of course, I told you the other time, statistics is like a story that goes on and on and on. Let me just prepare your mind. We're getting into situations that will require us mathematical or statistical complexity. But I just want to tell you, the moment you get yourself familiar with notations, symbols, and you're able to relate whatever notations, whatever symbols to real life, learning mathematical related discipline will be very, very easy. Okay. Let me just say this, what we want to start today will not be part of midterm 1. I told you, the midterm 1 we cover up to what we did from the day 1 to Monday. Of course, you have already, you have access to the midterm 1 practice questions, which I actually expect that you should get yourself familiar with those questions and the way those questions are answered, because that's basically going to be the trend of midterm 1. But it's going to be a class, I will dedicate a class to go over those questions with you before the midterm 1. Like I said, I want to welcome you to two-way analysis of variance. What we're going to be doing from now on is an extension of one-way analysis of variance. To have a recap of what we've done before now, one-way analysis of variance is actually being considered in a situation where I'm only trying to investigate the effects of one categorical factor on a response. Look at that, one categorical factor on a response. The name one-way ANOVA is actually derived from the fact that we put into consideration just one factor, except that what we're comparing is the levels within the factor. That's what we're comparing. We're comparing the response across the levels of one factor. But what if in a situation whereby, more than one factor explain the response? We always find ourselves in that situation most of the time. More than one factor explain a response. The focus today is when two factors explain a response, that will be called two-way ANOVA. When three factors explain a response, that will be called three-way ANOVA. Of course, what you see in display now, n-way, actually means if you have n factors, but let me tell you, all the factors here have to be categorical. If they are not categorical, you don't talk about ANOVA anymore. Okay, in the outline, I'm going to consider two-way ANOVA without interaction and two-way ANOVA with interaction. And of course, I'm going to tell you today what is the significance of interaction in two-way analysis of variance. I'm actually going to cite example from politics, from medical field, from psychology, and so on like that, for you to be able to understand. But let me tell you this, I will advise that you also cite your own example. My learning was so easy when I was in college. Whatever example or illustration given to me by my professor, I will never be satisfied until I provide my own example. When you provide your example, then you understand. Okay. I want to walk you, like I said, I've just explained what one way means, what two way means, what three way means, and so on like that. Would you take away from this page that I'm showing you now? In one way analysis of variance, you are only considering one factor with levels. Two-way analysis of variance, two factors with levels. The levels may be the same, they may not. Three-way analysis of variance, we are actually considering three categorical factors with levels. That's exactly what we mean. Then when you want to go beyond three level, of course, what determines the name you're going to give to the ANOVA depends on the number of categorical factors. Does that make sense to everyone? Okay, math is easy. Math is very, very easy. And statistics is very, very easy. But math and statistics are only easy when you follow it up with your mind. Not theoretical mind, practical mind. Then you're going to find it so easy. I'm going to walk you through the example that we started the other time. And I'm also going to cite more example. You remember the other time we actually considering the effect of sandwiches, type of sandwiches in attracting ants. We only consider one categorical factor, which is type of sandwiches. But do you know there are other factors that could also be put into consideration, like type of bread? Okay, like whether the bread, when they say type of bread, when we mean is it butter, whether the bread is butter or not. You consider type of bread, you consider whether it is butter or not. What if in a situation whereby we basically have that information? The first one is type of bread. We got 4 different types of bread. And whether it is butter or not, that's another factor, which is 2 category, yes or no. Okay, what if we now trying to figure out what effect, what I'm trying to show you now is more or less like putting into consideration, the factors of, 3 factors now. Look at that: filling, bread, butter, and each of them, they're categorical. Filling, we're talking about type of sandwiches. Bread, we're talking about the types of bread. Butter, we're talking about whether it has butter or not. Okay, and that is exactly what I'm trying to show here. Take a look at that. The fact remains that we still have one response, which is continuous in nature. Assumption, one of the major assumptions in using analysis of variance is that your response variable has to be continuous. When your response variable is not continuous, you are no longer doing ANOVA. It has to be continuous. And your independent variable, that I also call explanatory variable, that I also call predictor. Look at what I call it. We call it several names: independent, predictor, explanatory. We could also call it factor. We made it say they have to be categorical. Now, if we have 3 categorical predictor: filling, which is the type of sandwiches; bread, types of bread; butter, whether the bread has butter or not. Because don't forget, we basically want to see the attractiveness, the degree of attractiveness of type of sandwich. What if we also need to put into consideration the type of bread? Maybe ants don't just go to a particular bread. Maybe they have a preference for other breads. What about the bread that have butter or not? We basically we are going to have a treatment that are combination of these factors. When I consider the 3 factors, I'm doing 3-way ANOVA. When I consider only 2 factors, I'm doing 2-way ANOVA. Now take a look at this layout. Oh my God, this is a layout. What am I seeing in this layout? Look at the filing. That is type of sandwiches. How many levels? We got 3 levels. How many levels of bread do we have? Okay, we got 4 levels of bread. Now in this situation, this is a layout for situation, two categorical variable. Okay. But here is when I'm talking about when the bread, all the bread that I'm talking about here is they don't have butter. That's why you see, this is for butter equal to no. When I can also generate the one for butter equal to yes. And when I'm testing, also testing the effect of butter, yes or no, is going to make it to the factor. Okay. Now, I told you the other time, where we want to go into statistical analysis, we normally beat every statistician, every researcher, every data scientist. We behave like doctors. When a patient visits our doctor's clinic, the doctor will not start treatment immediately. You know that, right? The doctor will need to perform what I call some diagnostic testing. Why are they doing that? They basically want to figure out what is wrong with the patient before they basically going to use treatment. Let me tell you this, when you don't do your diagnosis very well, you're basically going to end up using wrong medication. Wrong diagnosis lead to wrong medication. And that is the reason why doctors normally do diagnosis before, that's why you see them running laboratory tests. They basically want to know, what is wrong. We also do that in statistical analysis. In statistical analysis, we call that data exploratory analysis, that we call descriptive statistics. What do we do in descriptive statistics? That is part of preliminary investigation, where we generate bus plots like this, where we're comparing. We actually want to have a sense of what is going on. Okay, take a look at this now. Of course, this is the type of sandwiches, as you can see. I've walked you through this before, right? So we took a decision that there's a significant difference, right? We use one-way analysis of variance, right? Because we focus on one factor. But let me tell you this one-way analysis of variance could be wrong, even though all assumptions hold. You know why it could be wrong? It could be wrong if an important factor is missing. A factor that also have effects on the response, like type of bread, like when the bread has butter or not. Now, this is a takeaway. When an important variable is missing in a model, it's basically going to induce a bias. Okay, it's going to induce a bias. Let me tell you this bias is the enemy, worst enemy of every researcher, every statistician, every psychologist, every sociologist that is into modeling. They will always want to reduce this guy. But what could cause this guy is when an important factor is missing in your model. If the type of bread is missing here, even though there's a significant difference among the type of sandwiches, we could mislead. Okay, now because of that, we want to put into consideration types of bread, which is another factor. This type of bread has 4 levels. And some of you may be wondering, if you want to go by this bus plot now, you're basically going to see like the mean are more or less the same. The mean of what? The numbers of ants, if you take a look at that. But graphical analysis is not alone to judge whether difference exists or not. We still need to conduct a standard statistical test. Now, if you take a look at the analysis that I want to perform now, I just want to do one-way ANOVA on breast this time around. Don't forget the other time, we did one-way ANOVA with a type of sandwiches, right? And there was a significant effect. But this time around, we also want to do one-way ANOVA with a type of bread, which is another factor separately. And what do we see? Oh my God, look at the p-value. Do you know that this p-value is in agreement with the bus plot? From the bus plot, I can see the difference is not that much. But look at the p-value. The p-value is trying to suggest that this p-value is greater than 0.05. the standard level of significance. So which means there's no significant difference among the levels of, the four types of bread used. There's an agreement now between the standard statistical result and the graphical analysis. Take a look at that. Do you know we may want to do the same on another factor separately on whether the bread has butter or not? This is going to be the third factor. And when we look at that, as you can see, the box plot is suggesting a difference, right? If you want to go by the mean, oh my God, look at the p-value. At 5% level of significance, we rejected, which means there's a difference between, no butter and butter. Look at that. There's a difference. And because there's a difference, you can see initially, when we try to investigate the effect of sandwiches, we notice a difference. When we investigate the effect of type of bread, there's no difference. But when we investigate whether the bread has butter or not, there's a difference. Then this is going to give us a sense that why not incorporating type of sandwiches and whether it has butter or not into the same model. Why do I need to pursue two-way ANOVA instead of conducting one-way ANOVA separately? I'm going to say that again. Why am I what is going to be gainful to research community instead of me to investigate the factors separately and investigating them simultaneously? What will I stand to gain? Oh my God, what I stand to gain is very similar to reason why you use one-way ANOVA instead of doing comparing independent t-tests. You remember the other time I told you, if I have three groups, why not use the idea of independent t-test, where you use difference of means? Why do you need to go for ANOVA? Of course, I told you we go for ANOVA in the first place because ANOVA will restrict your level of significance to 5%. When you decide to go, conduct independent t-test on two pairs at a time, your type 1 error will be inflated. And we don't want that to happen. And that is the reason why it's going to be gainful using, ANOVA, technique. Now, the same thing that we noticed then, it will be so gainful when we decide to simultaneously conduct, the effect of two factors at a time in a model. Let me tell you another, benefit. Another benefit, that could be interaction between the two categorical factors. Maybe the relationship between one categorical factor on the response may depend on on the effect of another categorical factor, which I'm going to demonstrate today with an example. Am I talking so fast or slow? Is there anyone here who is struggling with the way I talk? Is there anyone? Because communication is the key. Even if I happen to be a great professor, but you are not getting what I'm saying, it's like I'm making noise. I don't want to make noise. I want you to get the information. Be sincere with me. Okay? If you are not getting the information, please let me know. There's anyone that is struggling. Now, and that was why I said, is this analysis sufficient? Like, is this sufficient when I look at it one by one? When I look at the factor one by one, that is not sufficient. That's not okay. We can actually, we can actually look at the combination of factors in one model that will be gainful. Okay. Of course, I talk about interaction effects. Situation where two effects actually interact. And I gave an example here. It's just like, but let me tell you this: interaction could be good, it could be bad. For instance, if I mix mustard with hot dog, maybe mustard alone is bad. Pea hot dog, not so great. And, but by the time you had, when you add two things together, it's either it's going to give you something fantastic or something worse. But how are we going to know whether interaction work? We have a way to tell in statistics. We're basically going to test the interaction effect to see whether it is significant. If it is significant, it should be tolerated in our model. You know, there's something I'm actually going to do before I go into all this example. I think I still have a lot of time. I want to give example. I want to give so many example today. I'm going to give example from, you know, let me first start with agriculture. Somebody online, I think the video is having an issue. You may not be able to see, but I think I'm going to write later. Okay, so I'm going to cite example from agriculture. In agriculture, I'm talking about plant growth, right? The plant growth, this is the response. Okay, and I want to consider some factors. Okay, some factors like exposure to sunlight. You know, exposure to sunlight, we could have low versus high, right? And we're talking about watering frequency. Watering frequency. Maybe the watering frequency low, medium, okay, high. Now, how many factors do we have? This is factor number one, factor number two. Don't forget, each of the factor has levels. They don't necessarily have the same level. They may have the same level or not. Now, this is an example in agriculture. But let me tell you this, do you know we can also test the interaction effect of the two? Nobody knows whether the effect of exposure to sunlight on the plant growth may depends on the watering frequency. With that, we have to consider interaction effects in the model, because what if these two variables are the way they interact? I think it's the same thing as using chi-square in statistics to test whether two variables are independent or not. Independent or not means you are testing whether they got relationship. Okay, so this is an example in agriculture. Now you understand this example in agriculture now? You understand that? Okay. Now I'm going to give an example in politics now, where I want to consider I want to see whether the amount contributed to a political campaign. I want to see whether that amount varies according to political party and according to the level of income. So the level of income is basically going to be factor number one, and the political party will be factor number two. The level of income, maybe I have low, medium, high, and political party, if I'm talking about United States, maybe I'm talking about the Democrat, Republican, and Independents. And I may also want to talk about the interaction effect to see whether the amount contributed to, amount contributed may, in the particular level of income, it depends on the political party. You know, I actually like the way politics is being practiced in this country compared to the way it is practiced in where I came from. You know, we can here in this country, you are basically going to see somebody that is not in one particular party and decide to contribute for somebody in another political party. That's so interesting. What does that mean? The interaction is coming into play. We may test the interaction effect. I'm going to give you another example this time around from a particular company. Maybe in a particular company, the human resources may basically want to compare occupational stress, occupational stress. Okay, maybe the HR basically want to see whether the occupational stress varies, okay, varies across age, okay, varies across age and gender. Age, maybe there are 3 levels, maybe less than 40, maybe between 40 and 55 and above 55. And of course, gender, male, female. So maybe in a way, they're looking at the effect of gender on occupational stress, and they realize that that may depend on age. You can also consider interaction effect. Or if they want to, maybe if there's no that relationship, we can look at the effect of age separately. We can look at the effect of gender separately. So this is another example. Another example is maybe a particular company is introducing a new apple juice. Okay, new apple juice. And this new apple juice actually has 3 advantages over the conventional one. The advantages like it's cheaper, it has high quality, and convenience. Convenience. Okay, this is basically going to form marketing strategy, and the company is focusing on the response variable. It's actually sales, right? What if this particular, maybe the director, the marketing director is interested in which of this marketing strategy to emphasize on in advertisements? Okay, should we emphasize more on the cheaper aspect compared to the conventional one, or should we emphasize on the quality, or should we emphasize more on convenience? Okay, and because of that, not only that, they also want to consider another factor, which we call a media, which I'm going to call media strategy, which is going to be local TV and newspapers. Newspapers. Okay, look at that. These are 2 levels. This has 3 levels. They basically want to see whether the sales is going to be the same or different in local TV and newspapers. And let me tell you where the idea of interaction is going to come in. If it is anticipated or maybe observed that advertising, okay, maybe advertising any of this, let me choose the convenience. Okay, when they advertise convenience on local TV, maybe they record some lower sales, upper sales, depending on whether newspaper was used. Look at that, depending, which means the local TV, the sales, the mean sales when you advertise convenience on local TV is not the same when the newspaper is used, because when newspaper is used, it may be either less low in sales or high in sales. In that kind of situation, you're going to consider interaction. But let me tell you something. When you think about interaction, the only way that can be sustained, the only way that can be tolerated, the only way you can actually incorporate that into your model is when the p-value associated with the interaction effect is significant. Okay, now I want to come back. I think I've given you a lot of, you can think of your own example. Okay, now take a look at this layout. You know what I want to do here? I basically want to consider this like a 3x4 factors. 3x4. A factor A has 3 levels. Factor B has 4 levels. And in each cell, when I say cell, the cell is Y111, Y112. That is a cell for A1, B1. Interaction between, a level in factor A, which is A1, and a level in factor B, which is B1. How many observations do I have in that cell? I got more than 1. When I have more than 1, you must test interaction effects. But when you only have 1 observation in a cell, You don't need to test for interaction. I want you to take note of that. Okay, now I'm going to give you the meaning. And we're going to ANOVA notation now since we're working on two-way. I just show you the layout for two-way analysis of variance, having 3 levels of factor A and 4 levels of factor B. Take a look at that. And, in the model, what each of these actually represent, the file remain, I want my factor A to be type of sandwiches, and I want my factor B to be type of bread. Type of bread, we got 4 levels of bread. We got 3 levels of sandwiches. We're actually going to have some effect. If you take a look at A, that is going to be a numbers of group in factor A. I'm talking about a lowercase a. That will represent numbers of levels in factor A. In this situation now, type of filling is going to be 3, right? Lowercase b, numbers of group in factor B, basically going to be 4, and ij will be the sample sizes for file in I and j, and then I, the sample size for file in I, and then n dot j, the sample size for bread j. Please, I need you to internalize this. And what is an uppercase n? The uppercase n is basically going to be totality, the total number of observations that I have in all. Take a look at this. The y bar dot dot dot. Pay attention. When we're working with one-way ANOVA, it was y bar dot dot. But right now, we're talking about two-way ANOVA. It's going to be 3 dots. When you give me 2 dots in exam for two-way ANOVA, that would be wrong. Pay attention. It's going to be 3 dots. Okay? And when you have 3 dots, how many summation sign? It's going to be 3 summation sign. For 2 dots, 2 summation sign. Right now, that's why you get summation, summation, summation. The first summation is adding the levels of A, factor A. The second summation, adding the level of factor B. The last summation is talking about the subsample within a group, within a particular group. With that, you get your overall mean. Then the y bar ij dots. Y bar ij dots. That would be the sample mean of file in I. Bread J combination. What about y bar I dot dots? That would be the sample mean of file in I. You're going to have means from type of sandwiches. We're also going to have mean from types of bread. Play along with the notation y bar I dot dot. That is the sub mean within the factor A. Y bar dot j I. Y bar dot j dot. That's sample mean for bread j. So take a look at that. We want to go into a model. Oh my God, I'm presenting to you two-way analysis of variance model. Whatever we want to do in statistics, don't forget, let me remind you, we basically want to capture reality. What do we use in statistics to capture reality? It's model. You need to state your model. What if I ask you in exam? Okay, maybe I define a scenario that has 2 factors and possibility of an interaction. Oh my God, this is what you're actually going to write. This is a model for two-way analysis of variance where you're actually going to have a response yijk equal to the overall mean. The alpha high will be the treatment, effect that has to do with factor A, and the beta J, that will be treatment effect for factor B, and the combination alpha beta ij is acting as the interaction between the factor A and factor B. Oh my God, the error ijk now is the random part. Every specification of statistical model must have a random component, which is the error ijk. But every other term, apart from the error ijk, we call that deterministic part of a model. Deterministic. Every statistical model has a deterministic part and the random part. Now, I think I just gave you the definition, and don't forget, the error must follow normal distribution, which means the same way that we have assumption for one-way analysis of variance, we're also going to have the same assumption for two-way analysis of variance, which is going to go from assumptions of normality, assumptions of independence, and assumptions of constant variance. I think take a look at that. What is a mu cap? You know, you want to estimate the overall mean. That is just the meaning. Estimate of the overall mean. That's what we mean by mu cap. What is alpha cap? That is the estimating the effect of factor A. Oh, beta cap J, estimating the effect of factor B. Oh, the cap, you know, of the alpha beta high J, estimating the effect of the interaction. Before you can test for the significance of an effect, that effect needs to be estimated. Having a cap on each of that means you want to estimate them. Because the essence of having a model is to estimate every parameter in the model. So that is what we mean. Oh, I want you to take notes now, you know, because something like this may come out in midterm 2 exam. What if I, you know, the other time we do one-way analysis of variance, you know, using a regression way. And of course, I walk you through how to set up a design matrix X. If you want to do that, you know, you need to go back to the model. Okay. How many levels of alpha do we have? 3 levels, right? In the, you know, in the setup, we're basically going to consider 2. How many levels of beta do we have? 4, right? We're going to consider 3. Okay. Now I need you to take a look at this, right? Alpha 1, alpha 2, which means we're taking the degree of freedom for the levels of factor A. That was why you see alpha 1, alpha 2. Does that make sense to you now? Now, the beta 1, beta 2, and beta 3, it means we're taking the degree of freedom. Don't forget, how many levels of factor B do we have? 4. Therefore, what you're going to see, it's going to be 3 levels. I mean, in the module architecture. Oh my God. When you take a look at 2 by 3, it's going to be what? 2 times 3. That will be 6. Then it means alpha beta that you're actually going to have, there are going to be 6 of them. Any question on this side? That's why you say 1, 2, 3, 4, 5, 6. Now, how do we now set up? What if I ask you to set up the design matrix X? That's super easy. The first column, it means I need to get, you know, each of this column represent each of these. The first column is 1, 1, 1, 1, 1, 1. That's like a constant, an intercept. You're going to write 1, 1, 1 or 2, depending on the number of observation. The second column, it means I'm interested in alpha 1, which is like a group 1, right? If I'm interested in that, I'm actually going to have 1, 1, 1. Why do I stop at 4? You remember, why do I stop at this? That depends on a particular, you know, replication. So here I consider group 1, the other one. So group 1 here, I'm not considering group 2. Okay. So, or you can, if you basically want to write it, look at this. If I want to write this on the second and the third column, I can use the idea of 1, 0, 1, 0. If I'm talking about group 1, I'm going to say 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. That's for group 1. Okay. If I want to talk about group 2, that will be 0, 1, 0, 1, 0, 1. That is group 2. If I want to talk about the other group, then I'm going to use a negative. Okay. Now, what if I now want to talk about beta 1, beta 2, beta 3? 3 levels. I will use the idea of an identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. This is an identity matrix. I'm going to use that idea. The only thing I'm going to do is to repeat this depending on the numbers of groups. Take a look at that. Let's see. Oh, 1, 0, 0, 0, 1, 0, 0, 0, 1. Do you see that? So that is, if you see that 1, 0, 0, 0, 1, 0, 0, 0, 1, and the moment you write that, the next thing you're going to write is negative 1, negative 1, negative 1. And what you do here is what you're basically going to repeat. Look at that. That's what you are repeating. That is for B1, B2, B3. How will I get the interaction? The B1, this one means alpha 1 multiplied by beta 1. So what I'm going to do, the beta 1 is, I want to multiply second row, alpha 1 by beta 1, the second row and the fourth row. Second row multiplied by the fourth row, second row multiplied by the fourth row, 1 times 1, that's going to be 1. And that will give you this guy. Does that make sense? The multiplication within. Now with that, you set up the matrix X, okay? And of course, if I get the transpose of that, and I multiply the transpose by this, and I find the inverse, then I also use the transpose of this to multiply Y. There's going to be Y. Y is going to be the response. Then I'll be able to estimate orders. Okay? So I'm going to move now. In the two-way ANOVA, we believe that the sum of the effects, whether the main effect or the interaction, has to be equal to 0. Take a look at that. The sum of alpha I, the sum of beta j, the sum of alpha ij, okay, whether I sum that over the range of level of factor A or B, has to be equal to 0. And of course, I also need to determine the degree of freedom. If A minus 1 is the degree of freedom of factor A, and B minus 1 is the degree of freedom of factor B, don't forget, what do you normally do in interaction? We multiply. This multiplied by this with that of interaction. If I now simplify what I have here, that would be a B minus 1. So which means the numbers of factor in A multiplied by the numbers of factor in B minus 1 will be the degree of freedom, okay, for that. Now, the assumptions in one-way analysis of variance, I told you the other time, normal distribution, constant variance, independent observation. And what I'm presenting to you now, if I want to compute variation associated with each factor, as well as the interaction and the variation within as well, this is the formula. The first formula is how am I actually going to compute the variation within group A, within factor A. That's SSA, sum of square A. Sum of square B is the variation within factor B. Don't forget, in the one-way analysis of variance, we consider variation between groups. But here we're going to have 2 between groups, for A, for B. Then the third one for interaction. Then this SSE will be for within, okay? And the SST will be the total variation. Don't forget, the analysis of variance splits the total sources of variation into various components. And the advantage of two-way ANOVA over one-way ANOVA is just like when factor B is significant, you have succeeded in minimizing the error. Because when you use one-way ANOVA, your assumption is that the effect of any other factor is very small, and you put that in the error. But now that you bring it out from the error and it is significant, what will happen to the error? The error will be shrinking. And that is the motive of every statistician, every researcher. We basically want to minimize. We want to reduce the unexplained variation. Okay, now take a look at that. We're going to have an ANOVA table. Now the ANOVA table I'm presenting to you now is the ANOVA table for two-way ANOVA weight interaction, where you can see in the source of variation, you can see A, which is effect of factor A, effect of factor B, effect of interaction, the unexplained, and the total. When you then each of them has their corresponding degree of freedom. When you take a look at the second column, oh my God, A minus 1, because the numbers of factors in A is small a, lower A, then the degree of freedom will be A minus 1. The numbers of factor in B is small b, the degree of freedom will be B minus 1. The moment I know the degree of freedom for factor A, for factor B, I will be able to decide on the interaction, which is going to be the multiplication of the two degree of freedom. And the moment I got that, do you know the degree of freedom for total remain? If the totality is an uppercase n, the degree of freedom would be n minus 1. And of course, the degree of freedom for error would be N minus AV. And of course, the SS column is just talking about the sum of square for each of that. And the mean square column is the sum of square divided by the corresponding degree of freedom. Oh my God. If I get to F now, I'm basically going to be using the mean square for treatment A divided by that of the error. I'm also going to, so for B, I will get 3. It means I'm actually going to have 3F. When I get 3F, I'm going to get 3 p-values. Each of these p-value is to conduct hypothesis on what? Oh, they're going to be 3 hypotheses when you're talking about two-way analysis of variance. The first hypothesis will test whether the response is the same across the levels of factor A. The second hypothesis will test whether the response the mean response is the same across the level of factor B. And the third hypothesis will test whether the interaction is significant or not. And that is the reason why we are getting 3 p-value. And you're going to use each p-value on each hypothesis. Then you're going to take an independent decision. Now, this is a hypothesis now on my last page, because the focus on today is just to reveal to you the statistical architecture of two-way ANOVA. It is in the next class that we basically you're going to see how to do that in now, where I'm actually going to show you results. But what I'm just presented to you today is just a statistical model, statistical architecture. Look at the hypothesis 1. The hypothesis 1 is talking about interaction in this case, whether the non-hypothesis is going to say there's no relationship between 2 categorical factors, and the alternative is going to say there is. The hypothesis 2 is testing whether the mean of the response is the same across the levels of factor A. And why hypothesis 3 tests whether the mean is the same across the levels of factor B, which means in two-way analysis of variance, of course, we normally have 3 sets of hypotheses. But let me tell you this. If you look at hypothesis number 2, that we only focus on that hypothesis where we're dealing with one way, where we are we're comparing how attractive the type of sandwiches is. Now, when you now bring in a second factor now, which is a type of bread, if hypothesis 3 is significant, then it means we have succeeded in improving on the quality of the model in using the one-way ANOVA. And let us now also assume that the interaction is also significant. That would be another improvement. Let me tell you this. My time is up. Okay, this is going to be the end. Of course, that is going to be my last slide. Any question before I go? Any question? If you enjoyed today's statistical party, I need you to signify by giving me a thumbs up. Let me see. Do you understand? Oh, okay, I'm seeing. But do not hide your feelings. You still need to contact me if there's any area you don't really understand. Make sure you stay safe. And